In previous videos, we've seen how to draw Catmull-Rom curves. In this video, I'll talk about a couple of really cool things that you can do with Catmull-Rom curves. The first is tightening, or making the curve look like it's being pulled taut between the control points. The second is finding points on curves. By finding a point on a curve, you can move an object to that point and in effect make it follow the curve, which is the key technique for moving objects on curved paths. Let's first talk about tightening. I'll show you tightening in action, and this will show you everything you really need to know. Here's a Catmull-Rom curve made out of 8 control points. As you can see right now, the value of tightness is 0, and the curve looks perfectly nice. I'm going to start increasing the value of tightness now, eventually raising it up to the value of 1. Notice that the curve gets more and more taut, like it's being pulled tightly between the knots. When tightness reaches the value of 1, the curve is actually made up out of straight lines. I'll take the value of tightness now back down to 0, and we can see that the original loose shape of the curve is reappearing. Now I'll drive tightness negative. And notice that the curve looks like it's becoming kind of squarish. When we get to -1, it has a nice sort of squarish appearance. Now you might ask, what happens if we drive these values outside of the range -1 to 1? Well, you can certainly do it. Let's continue pushing the negative value further and further negative. Things become more and more square, and then something interesting happens. We start to get little loops at the edges and the corners, and the loops get bigger and bigger as tightness gets more and more negative. The same sort of thing happens if we make tightness much larger than 1. So here we are, we're coming back to -1. Now I'm coming back to 0, going back up to 1. Now I'm going beyond 1 in positive values, and you can see we're getting the loops again. The loops are becoming big and floppy, just like they did in the other direction. There's no hard and fast rule on how to use tightness. Generally speaking, if you stick between -1 and 1, you'll get a curve that looks like the curve you started with. But you can go crazy and use any value you like. The right value of tightness for your curve is the one that makes it look the way you want it to look. To control the tightness of a curve, you simply call curve tightness before you draw the curve, like you would call fill or stroke. Notice that there's a capital T in the middle. Curve tightness takes a single value. It's a floating point number, which here I'm calling S. As we've seen, changing the value of S changes how the curve tightness appears. When S has the value 0, we get the default smooth curve. This is the same as not calling curve tightness at all. When curve tightness has the value 1, the curve is drawn with straight lines. So this is the same as drawing the thing with straight lines. But of course, values between 0 and 1 give you something between these two extremes. When S is -1, we get kind of a squared off shape. Although generally it's a good idea to keep the value between -1 and 1, you can push it to the extremes. If you push S out to the positive extreme, like 5, we get a very loopy, knotty kind of a thing. If we push S to the negative extreme, say -5, we get a different kind of a big, loopy, knotty thing. Now let's take a look at points on curves. As I said at the start, this is all about finding a point on a curve, typically so we can animate an object moving along that curve. I'll show you this in action. Here's a simple Catmull-Rom curve with only 4 control points. The first and last points are in gray, the 2 middle points are in green. You can see the bright dot at the left, that's at t equals 0, or the beginning of the curve. As we hand processing values of t from 0 to 1, it gives us back points along the curve. So as the value of t goes up, the point along the curve moves until we get to 1, another point is at the far end of the curve. Just to show you what this might look like with a different shape of a curve, I'll kind of pull these control points around a little bit, and now we'll sweep from 0 to 1 again. And you can see we start at 0, we move our way all the way along the curve, and we end up at 1. So as we've seen, the basic idea is that if we have a curve and a value t, then a value of 0 will return the point at the beginning of the curve. As we increase the values of t, we get points along the curve. T goes from 0 at one end to 1 at the far end. So now I'll show you how to actually get the x, y values of these points. Let's create a little curve. I'll have points A, B, C, and D. Here's the curve that would go through them, and here's the curve that processing draws. Of course, we know to draw that thick curve between B and C, we can call curve, handing it the 8 numbers that are the XY values of the 4 points. But okay, let's get back to finding a point on the curve. I'm going to draw the axis for T. On the left, it's 0. On the right, it's 1. And I'm going to draw a little dot. So as I move this dot left and right, I'm choosing different values of t, and that will choose different points on the curve. When t is a little bit less than a half, as I'm drawing it here, we get a point that's sort of a little bit less than halfway through the big curve. I'm calling that xp, yp. Those variable names don't mean anything, they're just meant to be something short and distinct. How do we find xp and yp? Here's the technique. To find x, you call curve point with the x coordinates of the 4 points that are involved and the value of t. And we'll get back a single floating point number that is the x coordinate of the point in the red circle at the top. To get the y coordinate, we call curve point again, but this time we hand it the y values of the 4 points. Now this may seem a little bit weird, but it comes about because of how the mathematics of the curve is defined. So we only need one routine called curve point. We don't need a curve point x and a curve point y. This same routine curve point works for both x values and y values. So when t is 0, we get the point at the beginning of the curve, and as t works its way from 0 to 1, we get points along the curve until at 1, we're at the end of the curve. That's really all there is to it, but there is one little wrinkle that I'd like you to be aware of. Here's a simple Catmull-Rom curve. On the bottom, I'm drawing a horizontal line that represents the values of t. I'll start drawing some points on here for different values of t. Right now I have t equals 0 and t equals 1. Let's put one in the middle. Now I have t equals 0, 0.5, and 1. You can see from the bar on the bottom that the 3 points in t are equally spaced. So let's add a couple more points. But notice that the points don't look equally spaced on the curve. This is just the way Catmull-Rom curves work. The points tend to bunch up near the ends and not so much near the middle. Let me draw a whole bunch more points, and you'll see this in action. So there we are. It's really easy to see now that they're more spread out in the middle. This isn't just because I'm using this particular shape of curve. Here, I'll move the curve around, and you'll see it's still the case, no matter how I move the curve. In fact, even if the curve is a straight line, we still have this effect. Let's bring that up, and now I'll draw a fewer points, and you can see that they're still bunched up at the left end and the right end and spread out more in the middle, even though, as you can see at the bottom, the points are evenly spaced in t. Now, if this is a real problem for you, you can definitely address it, but it's a lot of work. Most of the time, we're willing to accept this, and if it really does look like a problem, we just take lots and lots of points, and we hope that the difference in their spacing isn't as obvious. Of course, the fewer points we use, the more obvious the difference is. In fact, this is sometimes even helpful. If you're moving an object along this curve, then having the points spaced more closely at the beginning and the end gives you kind of an ease in and ease out. The object starts moving slowly, moves faster in the middle, and then slows down at the end. So sometimes this is beneficial, but often it's not, and we just have to make do by either using a lot of points or living with their unequal spacing. If you want to find points on this curve, which perhaps we created by calling begin shape, end shape, and handing it all these vertices, remember that this curve is actually a bunch of little curves. Each one has its own range of 0 to 1. So if you want to find a point along the first segment, which I'm showing in green, then you would call curve point using a value between 0 and 1, handing processing the x and y values that make up that segment. If you want something that's along the blue part, then you hand it the x and y values for the knots that contribute to the blue segment and a value of t from 0 to 1. Same thing for the red, and of course, working our way around, each segment runs from 0 to 1. So if you want your point to sweep along this entire curve, you have to make sure you're handing processing the right batch of 4 control points and the right value of t that's running between 0 and 1 for that segment. Of course, tightness and curve point work together beautifully. If I run around this curve where the tightness is about 0, the point just runs around the curve. If I crank up the tightness to nearly 1, the point just bops around from one straight line to the next. If I crank the tightness way up and we start getting these loops, well, the curve just runs around the loops. Similarly, if I lower the tightness out to square land, the point follows the squarish curve. And if I push the curve way out until it's getting all loopy, well, the point still follows that. So you can change the tightness to be any value you want, and curve point will always give you back points on that curve.